Swayam Prabha. Digital India. Educated India.
Dear students, I welcome you back to another lecture under the lecture series on course material of Transportation Engineering 2. In the previous lectures, we have already discussed about one of the important components of any airport, that is runways. We have discussed about the various features of the runways in terms of the orientation of runways, the configuration of runways, the length of the runway strips, and the geometric features of the runways. In continuation of the same, in today's lecture we will be discussing about another important component of any airport, which is termed as taxiway. In the case of taxiway, we will be discussing about the taxiway requirements. We will talk about the length and the width of the taxiway, the transverse and the longitudinal grades, the side distance, and the design of the turning radius. So, we start with the taxiway and try to define that what is taxiway. The taxiways are defined as paths on the airfield surface for the taxiing of the aircraft and are intended to provide linkage between one part of the airfield and the another part of the airfield. What it wants to say is that we are trying to provide the connectivity for those aircrafts which are reaching or arriving on any of the airport, so that they can taxi on this particular lane away from the active runway strip on which the continuous movements are going on. And in that sense, it provides the connectivity between the different locations or different parts of any airport, and all those such connectivities are termed as taxiways. These taxiways have the aircraft movement, which are essentially ground movements. There is no air movement associated with these, and the movements are relatively slow. They are much slower as compared to the speeds at which the aircrafts have landed or at which they are going to take off. There are different types of taxiways. There is one type which is termed as the apron taxiway. The word itself defines that they are provided very near to the apron, so as to provide the storage of the aircrafts somewhere at the periphery of the apron, so that there is no interruption to the other movements of the aircrafts on the apron. So, that is what is the apron taxiway. The another type of taxiway is the dual parallel taxiway. Again, this name itself shows that there are two taxiways which are laid parallel to each other, and in this case there is one functional condition which is there, is that the taxiways can be exclusively used for a single directional operation. That is, on two taxiways we have two opposite directional movements, or the aircraft will be taxiing in opposite directions. Then the third type of a taxiway is known as the terminal taxi lane. This terminal taxi lane is provided very near to the terminal building, and it provides access to the terminal in terms of the access to the gate positions or to the stands where the aircrafts can stand, so as to take the passengers, or so as to just have the passengers who will be coming out of the aircraft. So, at that particular location, in between those locations, whatever the lane is being provided, that lane is known as terminal taxi lane. we now look at some of the factors which control the layout of any taxi lane or layout of any taxiway. The factors are that there should be a minimum interference between the just landed aircraft on a runway strip and the ready to take off aircraft which is coming towards the runway strip. So, it means there are two simultaneous operations which are going on. There is one aircraft which is landing, at the same time there is another aircraft which is ready to take off. So, a connectivity is to be provided in such sense that there is a minimum interference between these two type of operations and they cross each other with minimum hindrance. Further, there should be a provision of separate entrance and exit taxiway at various locations along the runway, and this is required so as to clear the traffic which is coming on the runway in terms of the landing aircrafts as soon as possible, and this will make them available for the other landing operation or for the another takeoff operation. And in this case, we can also provide the parallel one-way taxiway systems by which on one particular taxiway the aircrafts are coming towards the runway strip, whereas on the other taxiway the aircrafts are coming from the runway towards the terminal area. So, that is how the parallel one-way taxiways can be provided. Another important thing at the time of fixing the layout of the taxiways within the overall airport space is that there should not be any intersection of a taxiway with the active runway. The reason behind is that these two components have different speed conditions. The active runway is having the speed as much higher value, where the taxiways are having the speed of the aircraft which is quite low. Therefore, if there is an intersection, then this movement of an aircraft from on the taxiway from one side to the other side of the runway strip will cause delay for the aircrafts which are using the runway for say takeoff. At the same time, if there is a landing, then it may create a hazardous condition or may cause even an accident if such type of operation is going on an intersecting taxiway and the runway. Further, there is a requirement of facilitating the higher turn-off speeds for reducing runway occupancy and thus increasing the airport capacity. What it signifies is that the design feature of the connectivity of a taxiway with the runway. This design feature should help in facilitating the turn off at a much higher speed, and if this is possible, then with a little reduction in the speed of the landing aircraft, we will be able to take off the aircraft from the runway strip and it will come to the taxiway strip. This will help in reducing the overall occupancy time of any runway strip by an aircraft, and it means now the same runway strip can be used for another operation and thus the airport capacity will increase. Another point is that there should be a possible shortest distance between the terminal building and the end of takeoff runway. That is a thing which needs to be taken care if so as to provide the minimum travel from the terminal building to the runway strip at the time of taking off. Though we also try to have the similar sort of a condition for those aircrafts which are landing and which comes towards the terminal building or towards the airport stand to which they will be taken, so that the passengers can deboard. With this aspects in mind, now we will try to look up at the different geometric features of any taxiway. In the case of geometric features, we will be looking at the length of the taxiway, the longitudinal gradients, the rate of change of longitudinal gradients, the width of taxiway, the side distance, the transverse gradient, the width of the safety area, and the turning radius. So, these are the different geometric features which we will be looking at, and it is in the similar form as we have done in the case of the runway strips. Here in this photograph, we are looking at one of the operational area of any airport. In this photograph, we can see that there is a terminal building being provided on this side. This is a part of the terminal building being shown in this photograph. Then these are some of the extended pathways or the corridors which are coming out of this terminal building, which provides the connectivity to the aircraft, that is to the door of the aircraft. Now, this is the door of the aircraft as a block is spot being shown here. So, this corridor provides the connectivity directly to this level. So, the person who is coming from this terminal building do not have to go up or down, they can straightway move in this corridor and it will come up to this point. All these corridors being provided here, they are flexible in nature, means they can come, they can be stretched or they can be pulled back and will be placed up to this position because of these wheels being provided at the bottom, and they are sturdy enough so as to take the load of the passengers who will be coming from the terminal building and going through this aircraft. In the similar this case, what we can see is that there is a runway strip being provided on this side, and with respect to this runway strip, there is a connectivity provided at this one from this side through the taxi lanes. So, we have the two parallel taxi lanes being provided, and we can see that the aircrafts are moving in a certain direction. These aircrafts are moving in this direction, whereas these aircrafts are moving in this direction on these parallel two runway strips. Now, from these runway strips, these aircrafts will take a turn and they will come to this particular area, and this is another connectivity being provided between these taxiways and this one, and this is what is termed as the taxi lane, and this is a terminal taxi lane because this is provided very near to the terminal and provides a connectivity to the normal taxiway, and here the aircraft can go to this direction and can go to the other direction, and we can see that there are some aircrafts being shown at this location. We are standing with their nose in this direction, whereas in this direction here these are standing with the nose towards the left hand direction. So, that is how they are oriented towards different directions. This is another photograph being taken from the top, where there is a runway strip being defined here like this. This is one runway strip, and there is a parallel runway strip being provided at this location. So, we have the two parallel runway strips being designated as 25R and 25L. This 25R means for right and L means for a left condition. So, this is a right runway strip and this is a left runway strip, and this 25 defines the angle out of the 360 degrees at which this runway strip is being oriented. So, this is oriented at an angle of 250 degrees. This is the way it is being defined. 250 is defined here as 225. So, at the angle of 250 degrees, we have provided two runway strips on this airport, and in between these two runway strips, a central taxiway strip is being provided. What we have discussed previously as a requirement of the provision of the taxiway is that it should have the multiple access points to the runway strip. So, here we can see that very easily that this runway strip or this runway strip, they are being connected to the central taxiway by number of connectivities, and we can see the connectivities in this direction as well as in this direction, and similarly here in this direction or likewise. It means the aircraft which is coming from this direction as a landing can go away from this point or from this point to the taxiway, or if it is coming from this direction, then similarly it can go from this point or from this point or this point to the taxiway. So, it means on the basis of the propulsive power, if it is stopping in early condition, it can go away from the runway earlier, or if it is going to a little further distance, then it will come out of it at a further distance. And this is what is the main use of the connectivity of the taxiway with the runway strip, so that the efficiency of the runway strip and the traffic handling capacity of the runway strip can be enhanced. And if this can be enhanced, then the overall traffic handling capacity of the airport will also increase. With this aspect in mind, we start with the geometric features, that is the length. The length of the taxiway should be as short as possible. It will increase as number of taxiways have to be provided along the runway. As we have seen in the previous case, there was different connectivities, so it will increase the overall length of the taxiway. In the case of the longitudinal gradient, the level taxiways are operationally more desirable, that is the similar condition to the runway strips. If the gradient is steep, then it affects fuel consumption. This is again the similar sort of condition as we have discussed for runway strips. As per ICAO, the maximum longitudinal gradient is fixed depending on the type of the airport, and in the case of A and B type of the airport, it is designated as 3% maximum, whereas for C, D and E type of the airport, it is defined as 1.5% maximum. Then another specific feature related to the longitudinal gradient is the rate of change of longitudinal gradient. This rate of change of longitudinal gradient is controlled by the side distance available, and in that sense what we can say is that the available side distance on the pavement is affected by the rate of change of longitudinal gradient. So, it is a vice versa condition between the two things. Again, as per ICAO, the maximum change in the pavement longitudinal gradient is fixed as 4% for A and B category of airports, and it is fixed at 3.33% for the C, D and E category of airports. So, these are the specifications related to the rate of change of longitudinal gradient. In the same case, for the rate of change of longitudinal gradient, this change of grade should be smooth enough. It should not create any jerk position at the point where the connectivity is being provided, and if it is being done, then it will be a problematic condition to the movement of any aircraft across that point. So, that is why the smoothing is to be done, and this smoothing obviously can be provided by the use of the vertical curves, as we have seen in the case of runways, or we have also seen the same sort of conditions in the case of railways or the highways, means the concept remains the same. Therefore, the vertical curves of 30-meter length are provided at such junctions. So, there is another specification associated with this one, along with the rate of change. We are talking here about the vertical curve, and the length of the vertical curve is fixed at 30 meters. Now, in the case of airports which are designated as by letter A and B, again ICAO recommends the length of the vertical curve as 25 meters for each 1% in the grade change. So, if there is more percent of the grade change, then with respect to that we multiply it with 25 meters so as to get the length of the vertical curve. Whereas, in the case of the airports where they are being designated by the code letters as C, D and E, then ICAO again recommends the length of the vertical curve as 30 meters for each 1% change in the grade. So, these are the specifications with respect to the type of the airport and the value which is recommended as a rate of change, along with the length of the vertical curve and the overall value which is to be provided in this case. Then the similar conditions are there with respect to FAA. FAA recommends the distance between the points of grade changes. This is what we have seen when we have seen a diagram of the change of grade from x to y to z, that is plus x to minus y to plus z, and then there was a change in the gradient from x to y designated by A, and then there was a change in gradient from y to z designated by B. And the similar sort of condition for the taxiways, the FAA defines that this value can be 30 times of A plus B, and this A plus B is being taken in the absolute form where the effect of the positive or the negative value is being taken away. So, these A and B, they are the percent grade changes at the 2 points of grade changes along the center line of the taxiway. So, this is another recommendation and the guideline being provided for the provision of the different grades, and then at the same time so as to maintain a distance between those changes of the grades. Now, we come to another geometric feature of the taxiway, and that is the width of the taxiway. The width of the taxiway is lesser than the width of the runway. The reason behind is that the aircrafts are not airborne and the speeds are small in this case. Therefore, we can control the movement of the aircraft as compared to the movement on the runway, because with the small change in the controlling feature of the aircraft when it is coming on the runway and moving at a higher speed, then it may be a disastrous condition, whereas in the case of the taxiway, because the speeds are very less, the steering of the aircraft will not create any big effect in the case the width of the taxiway is being provided lower. Further, there is not much variability in the maneuverability of the aircraft. That is a thing which I was just discussing, is that if it is a sort of normal movement of the aircraft on the taxiway in a certain direction so as to reach the destination, that is the terminal or the runway. And in this case, the nose of the aircraft mostly follows the taxiway center line. That is the one type of the guideline which is being provided, that the pilot may follow the center line of the taxiway and the nose will keep on moving along that one, and in that case whatever is the width being is required, that width is to be provided. Generally, this width of the taxiway varies between 22.5 meters and 7.5 meters. Then as far as the ICAO recommendations are concerned, for the width of the taxiway, what we look is that it is defined in terms of the airport category, and if the airport code is A, then the taxiway width is 7.5 meters. If it is B, then it is 10.5 meters. If it is C, then it is 15 meters, and it is at times provided as 18 meters if the taxiway is used by aircraft with a wheelbase equal to or greater than 18 meters. In case of a D category of the airport, the value is 18 meters, and similarly here also it is enhanced to 23 meters if it is used by an aircraft with an outer main gear wheel span equal to or greater than 9 meters. In the case of category E, this value is 23 meters. So, these are the various categories of the airports for which the taxiway widths have been defined, and these varies from 7.5 meters to 23 meters. Now, another specific geometric feature of taxiway is the side distance. As we have discussed, this side distance is more important at the connectivities. As the speed of the aircraft on taxiway is lower than the speed of the runway, the smaller value of side distance is sufficient on the taxiway. we know that as we have computed the value of the side distances from the very starting when we have read highway engineering, and there we have seen that as the speed keeps on increasing, the side distance keeps on increasing, and it becomes something like 180 meters at a speed of 100 kilometers per hour speed, whereas at a speed of 40 kilometers per hour the side distance requirement is around 50 meters. So, in the similar form here, when we are looking at the taxiways are being governed by the lower speeds of the aircrafts, and therefore the requirement of the side distance is also lower. ICAO recommends that the surface of taxiway must be visible at least up to a distance of x from any point at a height of y above the taxiway surface. That is what ICAO recommends, that if we are at any point and we are at a height of y above the surface, then we should be able to see up to a distance x. And how these x and y have been defined by ICAO, we will look at those values. They have been defined with respect to the airport code, that is the categorization of the airports. And here for the airport code of A, the y value, that is the height at the above the pavement surface, is 1.5 meters, and in this case the side distance should be 150 meters. Whereas in the case of airport code B, the height is 2 meters and the distance is 200 meters. For a C, D and E category of the airports, the height is 3 meters, whereas the distance is 300 meters. Now we look at transverse gradient. This is another type of the gradient which needs to be provided, which needs to be considered when any of the geometrics have to be taken up. And the conditions remains the same as we have talked about the runways. They are adopted on the same recommended conditions like runways. Basic thing is that they are provided so as to drain off the water and so as to bring the taxiways again to the dry condition, so that there is no slipping, there is no ponding of water on the taxiways, and which may be detrimental and which may be hazardous for the movement of the aircraft on the taxiways. ICAO again recommends the maximum pavement transverse gradient of 2% for A and B category of airports, whereas in the case of C, D and E category of airports, it is being defined and designated as 1.5% again by ICAO. Then there are some recommendations which have been given by FAA, and FAA says that the transverse gradient of at least 3% is to be provided for shoulders which have been turfed, being provided with some fixed objects, and also a 4 centimeter drop from the paved surface to the graded shoulder surface should be provided. That is another recommendation being given by FAA. The minimum gradient in the case is being taken as 0.5% for the rigid pavements and 1% for the other pavements. This remains the same as in the case of the runway strips, because here as well as there the concept remains the same, and that is the drainage of water. Now further, there is values being defined by ICAO, where the minimum transverse graded portion is being defined for maximum transfer value is being defined for the various air drum codes ranging from A to E, and in this case if the graded portion is in the upward direction, then the values ranges from 3% to 2.5% starting from A to E. If it is in the downward direction, then we found that it is being provided in a constant form as at a rate of 5%. Similarly, in the case of ungraded portion, If it is in the upward direction, the value remains as 5%. The other thing which we have to look at is the safety area and the width or the total space which is to be provided for the safety area. A safety area here is made up of partially paved shoulders on either side plus the area which is graded and drained. And in this case, as we have seen in the case of runways also, that we have to look at the area which is provided on the two sides as well as the area which is to be provided on the ends. In case of the jet aircraft, a paved surface of light strength material on either side of the taxiway edge with a minimum width of 7.5 meter is to be provided on both sides of the pavement edge. Therefore, whatever is the width of the taxiway lane, that is defined in terms of varying between 7.5 meters and 23 meters, then on the side of that 23 meter taxiway lane, we can provide the 7.5 meters on one side and 7.5 meters on the other side. That means 15 meters more, and that is what becomes the overall safety area. Now we look at the width of the safety area. That is another geometric feature. In this case, the pavement thickness should be thick enough to support the airport, patrol vehicles, etc. That is one thing. Another thing is that the surface should be treated with bitumen and it should not disintegrate due to hot blast of the jet aircrafts, and the surface should be smooth and impervious. We have already seen that what should be the size of the width of the safety area, but apart from that, there are certain things which needs to be taken care of with respect to pavement thickness that have been enumerated at this point. Then as per ICAO, we have some of these values like the pavement and shoulders. They should be 25 meters wide in the case of category C, 38 meters for category D and 44 meters in category E. Whereas the edge safety margins, they should be 1.5 meters for category A, 2.25 meters for B, 3 meters for C, 4.5 meters for D and 4.5 meters again for E. In the case of graded portion of the strip, the values are 22 meters for A category, 25 meters for B category, again 25 meters for C, 38 meters for D and 44 meters for E category of aerodromes. Now here this value of 3 meters being provided for the edge safety margins in the case of C category of the aerodromes, this may be 4.5 meters if it is intended to be used by an airplane with a wheelbase equal to or greater than 18 meters, means it will become similar to the category of D and E. Whereas in as per the guidelines given by FAA, it is being defined on the basis of the airplane design group, which ranges from 1 to 6, and here the width of the safety area will be 15 meters for category 1 and it is 24 meters, then 36 meters, subsequently to 52 meters, 59 meters and 79 meters in the design group category 6. Then in the case of edge safety, it is 1.5 meters for the first case, 2.5 for the second category, 3 meters for the third category, 4.5 meters for fourth category, again 4.5 meters for fifth category and 6 meters for the sixth category. Then we have the shoulder width, which is 3 meters for first and second categories, 6 meters for third category, 7.5 meter for fourth category, 10.5 meters for fifth category and 12 meters for sixth category. Now we come to another important aspect of the features of taxiway, that is the turning radius. This turning radius is the thing which provides the transformation or the movement from the runway to the taxiway, that is from a high speed to a low speed condition. and therefore we have to adjust the turning radius in such a way that it provides or it makes it possible so that the aircrafts can take a turn at a higher speed to the taxiway and come to a lower speed condition. So, in that sense we have to see that the change in the aircraft path is done by providing a smooth horizontal curve, and the design should be such that the aircraft can negotiate the curve without significantly reducing the speed, because at the time of the change from the runway to this taxiway through the connectivity, that is the circular curve being provided, at that point of a time there should not be a much change in the speed. Whatever is the speed with which it is coming, the aircraft is coming, it should be able to negotiate. The recommended radii corresponding to the taxiing speeds of small subsonic and supersonic airplanes is 60 meters, 135 meters and 240 meters respectively. If we have the planes which are having a speed less than 1 Mach, that's 135 meters, but if the speed of the plane is more than the Mach number, then it is 240 meters. The relationship between the exit speed and the radius of the curve is ascertained, and this value can be computed by this formula. The radius is V square divided by 125 F, and this value will come out in meters. Here V is in kilometers per hour and F is the coefficient of friction and is equals to 0.13, that's it is being fixed. So, we have the fixed value of F, this is another constant as 125. Therefore, there is only one variable which governs the radius, and this is the speed at which the aircraft is taking a turn. So, this is a turning speed, not the speed at which it is moving on the runway. So, this turning radius, this is how we define it here in this diagram. There is say the supersonic aircraft, means an aircraft which is coming at a much larger speed as compared to the normal conditions, and we have this center line condition. So, what happens is that in this case, if this is the 60 meter radius at which it is being provided, and this is the center of the nose gear following the center line of the taxiway, means this nose gear is trying to follow the center line of the taxiway being provided like this. So, this is what is the condition, and then there is another pathway being shown on this side, and this pathway is the path of point midway between the main gears. So, the nose, what happens is when the pilot is trying to maintain the nose along the center line, then the two gears which have been provided, one on this side and the one on this side, they will be trying to maintain adjusting themselves in this one, and this will be the center line of those two main gears, means there will be one wheel which will be moving somewhere here, and there will be another wheel which will be moving somewhere here, and that is how they will keep on moving on the two sides of this particular center line. So, there is a such sort of orientation which will be there, and therefore, we have to provide this curve in accordance, so that this aircraft is not going away from the edge of the taxiway pavement. So, that is the main thing which is to be maintained, and this type of condition should not get created. We will also look at some more diagrams here. This is another diagram where we can see a plane which is coming on this side, and this is the runway strip on this direction, and this runway strip means the this aircraft is coming along the center line of this runway strip. So, this axis of the aircraft is just superimposing on the center line of the runway strip, and then as this connectivity is being provided, so we have this center line like this. So, this is the center line of the curve, this one, and then this is a position which is being taken by the aircraft after taking the turn on the taxiway, and again it is aligned with the center line on this taxiway with the wings coming out in the safety area. So, what is happening here is that this nose gear, it tries to track beyond the intersecting taxiway center line. That is, this is a condition where what it is trying to do is that this is a judgmental approach of the pilot. The pilot is trying to move the nose of the aircraft along this pathway, the red pathway being shown here. This is on the basis of the judgment of the pilot. What he is trying to do is that this particular gear, which is on the inner side of the curve, this is moving like this, and while this particular movement, it should remain clear of the edge of this connectivity. That is what is the basis of this particular judgmental oversteering method, or judgmental oversteering being done, adopted by the pilot. So, in this case what will happen is that if this nose will go away from the center line like this is the center line. So, this is going away from the center line, and then after negotiating this curve, this will come back to the center line, and the aircraft will get oriented again with respect to the center line. So, only part here to emphasize is that because this gear is not going away from the edge, therefore, the smaller size of the fillet may help us in this particular location. So, we have this particular hedged portion being shown. This is what is termed as the fillet, and this is the fillet, means this is the extra area which is being filled, so that if there is any emergency, then this can be utilized by the moving aircraft. This is another diagram where again this is a runway strip, and this is the connectivity, and this is the taxiway. So, this is the center line of the taxiway, this is the center line of the runway, and here it is being provided, or it is being connected by this circular center line of this curve. Now, in this case here this is tracking where the pilot is trying to keep the nose along the center line of the connectivity. So, it means that nose will be taking the same profile as being provided by the connectivity of the center line, that is this particular one. So, the nose is coming in this form, this is coming along this one, whereas in this case this is one wheel and this is another wheel being provided on the two sides of the wings. So, this is going in this pathway like this, whereas the another wheel will take a path like this, and here it will, in this particular portion, this is superimposing with the nose gear pathway, and again it is going away from this one, so that it becomes a central position in this location. The main thing to see here is that this particular wheel is making making a change from in this direction like this, and here this is the edge of the curve, whereas the pathway of this particular wheel or this particular gear is going away from this edge like this. So, this line is showing the pathway of this particular gear. It means it is going away from the edge. So, that is the disadvantage in this particular method, where if we are following the center line profile along the nose, then the inner side gear may go away from the edge of the curve, and therefore, we require a much wider fillet to be provided in this case as compared to a very smaller fillet which has been required in this case. So, that is the differentiation between the type of the turning radiuses and the type of the movements on those turning radiuses which can be there when the aircraft moves from the runway strip to the taxiway strip. This is a condition for a U-turn, where this is a runway and this is a taxiway, and the aircraft is coming to the end, and then it has to take a turn so as to go to the terminal building. So, in this case again there is center line to center line nose tracking. Therefore, means this nose of the aircraft keeps continuing moving along the center line like this, whereas there is one wheel on this side and there is another wheel on this side. So, this wheel will be making a turning like this and this wheel will be making a turning like this, and in between in this particular section there is an overlapping of the outer gear with the nose gear path. So, this is the overlapping. So, in this case also there will at this particular location the inner gear is touching the edge of the taxiway, and therefore, we require to provide a fillet in this orientation at this particular location. So, this is another type of movement and another type of curving conditions which needs to be just understood. This is another case where it is coming from say one of this condition to this one, and this is ICU recommended condition where it says that this is a nose and this nose is going very near to the approximate path of the nose gear remains very near to the center line, and this is once it is being done, then again this inner side of the gear will go inside of the curve, and therefore, a wider fillet is to be provided with the radius here it is being talked of 30 meters. So, there is a modification of the fillet to be provided. This is known as cockpit following center line of turn method as recommended by ICAO, that is cockpit following center line of turn. So, what we found is that according to Horenzev, for supersonic aircrafts, the radius of curve should be such that a minimum distance of 6 meter is maintained between the nearby main gear and the edge of pavement. That is the premises, that is the principle or the concept which is being taken by the Horenzev. So, clearance is 6 meters, and in this case the radius is given by 0.388 square of W divided by the difference of 0.5 T minus S, and in this case according to Horenzev, this R is the radius of the center line of the taxiway in meters, W is the wheel base of aircraft in meters, T is the width of the taxiway pavement in meters, and S is the distance between the point midway of the main gear and the edge of taxiway pavement in meters again. So, this is how the values have been defined for this turning radius, and this S is taken as this value of distance between the point midway of the main gear and the edge of the taxiway pavement is computed as 6 plus wheel thread divided by 2. This wheel thread we have already discussed. This is the distance between the two main gears being located below the wings. Now, we come to the fillets, and the fillets are the extra wide areas as we have seen already, which are provided at the curve and traffic lane intersections, so that the rear wheel does not go off the pavement edge. So, that is what is the function of the fillet, and the minimum radii of the fillet is dependent on two things. One is the angle of intersection of the traffic lanes, that is the runway or the taxiway, or the taxiway or the taxiway, or the runway or the runway, and the wheelbase of the turning aircraft. If the size of the aircraft is big, the wheelbase will be big, and therefore, it requires a bigger turning area, where if the size of the aircraft is smaller, then the wheelbase will be also smaller and it can take a turn in a very small area. So, that is why the requirement of the fillet is governed by both the things, the specification of the aircraft and the intersection of the angle. The radii is not specified for wheelbase greater than 20 meters, and it is to be determined graphically using the path of nose gear. what we found is that for an angle of intersection between 0 and 45 degrees, the radii of fillet in meters for a small airport is defined as 7.5 meters, for large airport is taken as 22.5 meters. Whereas, if the angle of intersection varies between 45 degrees and 135 degrees, then the value for a small airport is 15 meters, whereas for large airport it is 30 meters. Then if the angle of intersection increases and it becomes more than 135 degrees, then the radii of fillet is 60 meters for small airports and it is also 60 meters for the large airports. This radii of fillet should not be less than the width of the taxiway. That is the another thing which is to be considered. Now, we look at the fillet for the different conditions. Here in the case of the small airport, we have the runway strip and this is the taxiway. So, the here what we found is that the turning is greater than more than 135 degrees. This is the turning angle more than 135 degrees. In this case, the radius should be 60 meters at this particular location, where at this particular location it is governed with respect to the angle, that is 45 degrees, and therefore, this radius is 7.5 meters. Whereas, this is another condition where we have the runway being connected with the taxiway. Here the angle is between 45 and 90 degrees, therefore, the radius is 15 meters, and this angle is between 90 and 135 degrees. So, for that condition also this radius remains 15 meters. So, that is for the small airport condition. In the case of large airports, what we see is that again it is 135 meters, the R remains 60. If it is less than 45 degrees, then it becomes 22.5 meters. This is another diagram as we have seen for the smaller airports also. It is for 45 to 90 meters, the radius is 30 meters as shown here, and similarly for 90 to 135 degrees, the radius again remains 30 meters. So, this is the typical diagrams or typical connectivities which can be provided. Now, we look at the another aspect, that is the separation clearance between the taxiways which needs to be provided, and this depends on the navigational aids, the type of the airport and the wingspan. These are the three factors which will control the separation clearance. As per FAA, the separation clearance is based on wingspan, and in the case of taxiway center line to taxiway center line, it is taken as 1.25 times of W, where W is the wingspan plus 2.1 meters. Whereas, in the case of taxiway center line to the obstacle, it is taken as 0.75 times of the W plus 2.1 meters. For apron taxiway center line to obstacle, it is taken as 0.63 W plus 2.1 meters. So, this is how we can compute the separation clearance based on wingspan as given by FAA. Further, it is also being defined by FAA in terms of the design item and the airplane design group, and for the taxiway center line to the parallel taxiway center line, it is 21 meters for category 1, and then it is 31 meters, 46 meters, 68 meters, 75 meters and 102 meters for final category 6. Whereas, taxiway center line to the fixed or the movable object, then this value is or the property line, then this value is 13.5 meter or 20 meters, 28 meters, 41 meters or 46 meters or 61.5 meters for airplane design group category 6. Further, in the case that we are taking the distance from the taxiway center line to the fixed or immovable object, then the range of the separation clearance varies from 12 meters in the case of design group 1 to 51 meters in the case of design group 6, and we have the values as 16, 25, 36 and 39 in between. For the distance between the taxiway center line and the runway center line, then the values most of the cases are 120 meters, In the case of group 6, it is 180 meters, whereas in the case of group 5, it varies with the airport elevation. In terms of ICU guidelines, it is the minimum separation is defined as per the aerodrome code is concerned, and in the case of edge safety margin, this is 1.5 meters for A, 2.25 meters for B, 3 meters for C, 4.5 meters for D, and 4.5 meters again for E. Whereas from the taxiway center line to the taxiway center line, it varies from 21 meters in the category A to 81.5 meters in the category E of aerodrome code. Whereas if it is a distance between the airport taxiway center line to the object, then this varies from 13.5 meters for aerodrome code category A to 49 meters for aerodrome code category A, with the intermediate values as 19.5, 28.5 and 42.5 meters. In case of the aircraft stand taxi lane, then this value ranges from 12 to 42.5 meters, with values in between as 16.5 meters, 24.5 meters and 36 meters. We have some more values here, and this is the minimum wing tip clearance, which is 3 meters for A and B category of aerodromes, 4.5 meters for C category of aerodromes and 7.5 meters for D and E category of aerodromes. Then in the case of stand safety margins, it is 1.5 meters for A and B, 2 meters for C category and 2.5 meters for D and E category. In case we are going to intend for an aeroplane with a wheelbase equal to or greater than 18 meters, then the value of 3 meters can be changed by 4.5 meters for a category D. The minimum separation between the parallel taxiway center line or the taxiway center line is given by this equation, that is the separation between the taxiways is equals to W plus 2U1 plus C1, whereas the required separation between a taxiway center line or an apron taxiway and the fixed or movable object is given by, this is T and O, that is object, then it is 0.5 W plus U1 plus C2. And there is another one case where we have the separation between an aircraft stand taxi lane and the fixed or movable object. In that case, it is given by 0.5 W plus U2 plus C1, where these values of U2, C1, so whatever abbreviations have been used are: W is the wing span of most demanding aircraft, U1 is the taxiway edge safety margin, C1 is the minimum wing tip clearance, C2 is the required clearance between wing tip and object, and U2 is the aircraft stand safety margin. So this is all about the taxiways and the provision of taxiways and their requirements and the design features. So in today's lecture, we have tried to look at the geometric features as well as we have tried to look at the connectivity of the taxiway with the runway using fillets and the radius. We have also looked at the separation clearances which needs to be provided between the parallel taxiways or the taxiway and objects or the taxiway or other movable things. With this, we stop in today's lecture, and we will be looking at in some of the other features of the taxiway in the next lecture. Till then, goodbye and thank you to you.
Thank you.